Let's finish out this unit by taking a look at an example. So we're given that some current distribution has given rise to the vector magnetic potential A, and A is given here as x squared y in our x direction, y squared x in our y direction, and minus 4xyz in our z direction. And we're given that that's in units of Webers per meter. And we want to calculate two things. We want to calculate our magnetic flux density B at point -1 to 5. We also want to calculate the flux through the surface z equals 1 for x between 0 and 1 and y between -1 and 4. So as always, I encourage you to pause the video and work through the example by yourself before coming back to see the solution here. So for part A, our approach is that we're going to find a general expression for B using our equations that relate B and A, and then we're going to plug in these specific values. So let's go ahead and set that up for part A. So we know that our magnetic flux density B is just equal to the curl of A. And so thankfully this is in Cartesian coordinates, so it's not going to get too messy. So let me just, for completeness, write out this definition. So the curl of A in Cartesian coordinates is going to be the partial of the z component with respect to y minus the partial of the y component with respect to z in our x direction. So sort of an easy way to remember these is we see that because this is our x direction, we have our z and our y and no x in that area. We also note that the later letter z is coming first up here, and then we're doing y second. So again, sort of just little tricks to help remember this if you ever need to. So then for our second term, again, this is going to be in our y direction, so we're only going to have x and z in this bracket. So we're going to have the partial of the x component with respect to y minus the partial of our z component with respect to x. And this is in our y direction. And then finally, we have the partial of our y component with respect to x minus the partial of our x component with respect to y, and that's in our z direction. And again, this can be referenced from the back cover of the textbook. You'll have it in your note sheets. I'm not expecting you to memorize this, and I've noticed I have an error here, so this should be partial with respect to z in this middle term. But be able to apply it, so that's the important thing. So of course now we come up here and we say, well, this is our x component, so this is our ax, this is our y component, our ay, and here, including this negative sign, is our z component, a sub z. So now we just plug into that expression down there, taking those partial derivatives. So relatively simple equation, but if you have questions about any of these resulting numbers, let me know. So the partial of z with respect to y ends up being a negative 4xz minus partial of y with respect to z is 0 because we had no z dependence, and all of that is in our x direction, plus, now for this first term we also get 0 because there is no z component in our a sub x, minus, now we still have that negative sign, we don't want to forget that. This ends up being 4yz, the partial of z with respect to x. All of that is in our y direction. Plus, finally, we have our partial of our y component with respect to x is y squared. And so let me see if I can keep both of those on the screen so you can see those both at the same time. And then finally, we are subtracting from that, we get x squared. When we take that last partial derivative, all of that is in our z direction. Again, if you have any questions about that partial derivative or plugging in, let me know. So now we can, of course, clean this up a little bit, and we can say that our magnetic flux density B is equal to, and I'll use angle brackets, and I can say in our x direction we have negative 4xz, in our y direction we have 4yz, and in our z direction we have y squared minus x squared. And that is going to be in units of Webers per square meter. Okay, so here is our general B expression, but our problem had asked us to find B at a particular point. So of course, all we need to do is plug in -1 for x, 2 for y, and 5 for z into this general equation. And what we can find is that our B at that point of interest, so at -1 to 5, we find that our B is equal to 20, 40, and 3. And of course, our units are still going to be Webers per meter squared. Okay, so that's our answer to part A. So now for part B, there are actually a couple different approaches, and we're going to talk about both of them, but only solve one. So first, let's go ahead and visualize what we're dealing with here. So we have part B, and let me go ahead and copy, or paste rather, this sketch of our surface that I sort of had prepared ahead of time. So we notice we're talking about the z equals 1 plane, so this is z equals 1, and it's between our x equals 0 and our x equals 1, and we also have y limits of -1 to +4. So I've tried my best to sort of represent that in 3D. Again, hopefully that's clear enough, but if not, try to make adjustments or maybe redraw yourself. So what we want to know is the flux through this surface. So of course it's not a closed surface, so we know it doesn't necessarily have zero flux, and we see that we have some magnetic flux in the region, so it's probable that it's not going to be zero. One thing that the problem is not clear on is that it doesn't specify a direction for the flux. So we can define flux as going up through the surface, or we can define flux as going down through the surface. And so in this case, we're kind of left with some freedom. We can define this either way since it wasn't defined in the problem. If we want to define our flux as going upward, we're going to need a ds vector pointing upward in this direction. So that's going to be perpendicular to the surface. We could call that, for instance, ds1. Now, if we want to deal with flux going downward, and so let me go ahead and make a note here. So let's say this ds1 is for an upward flux. Now, if we want our flux to be downward, defined downward, what we would do is we would just have a vector coming off the bottom, ds2, and again, that would be perpendicular. And so we would use that ds when we were calculating our flux equation. So that is our, if we wanted to define our flux as going downward. Okay, so let's, and again, we could arbitrarily choose this since our equation didn't, or our problem did not specify. But if we come up here and we look at this general form of B, particularly at the z component right here, because again, we're talking about flux going through the surface, so that's going to be either in the positive z direction or negative z direction. In the ranges that we're talking about, so x between 0 and 1, y between -1 and 4, this z component is typically going to be positive. So if we want our overall flux psi to be positive, then we can choose the ds1, and that's going to give us a positive flux. Does that mean we have to choose that? Absolutely not. We could choose ds2, and we're going to get the same magnitude, just a negative sign out front. So here what we're going to do is, let's say we're going to choose ds1. And so again, we can go back to our vector calculus stuff, and we can figure out our differential surface areas. And so we know in Cartesian coordinates for this particular plane, our ds1 is going to be dx, dy in the z direction. And the only difference is our ds2 would be dx, dy in the negative z direction. Okay, so let's take that information and go back to our general flux equation. So we know our flux is equal to the integral over the surface of b dot ds. And so now remember, our b had these three components, but because it's being dotted with something that has u of z, only the z component is going to come out. So we're going to have a double integral for this surface. So our y is going from -1 to 4, our x is going from 0 to 1, and we only have that z component, which is y squared minus x squared, and our differential surface area magnitude was dx dy, because of course we had u of z dot u of z, which is equal to 1. Okay? And so now we can just evaluate that. So what we would do is, of course, just split this into two integrals. So we have our integral from y equals 1 to 4, integral from x equals 0 to 1 of y squared dx dy, minus the integral from y equals -1. Sorry, this should be a -1 over here in our first double integral, to 4, and x equals 0 to 1 of x squared dx dy. And so if we go through and evaluate that, what we end up seeing is that we have our overall flux psi ends up being 20 Webers. And so again, if we had chosen ds2, The only difference is that we would have had negative 20 Webers. The same way if we defined current going through a wire left to right, it would be the same magnitude, just a negative value if we had defined it differently going from right to left. Okay, so one last thing to note then is that we do have an alternate equation for our flux. So we could have used that alternate equation as well. So we could have used that the flux is equal to the integral around the closed path L of A dot dl. Now, in this case, it's a little bit more work, not too much, but one maybe reason we would want to look at this equation is our A value, our magnetic potential vector A, was the given information in the problem. So potentially, we make some mistake calculating our B, and so if our B equation is incorrect, particularly that Z component, then we would end up calculating an incorrect flux. So it could be advantageous to stick with just our given information as we see here. However, in this case, it's a little extra work, so that's kind of up to you. One important thing to point out, though, is that the direction of this dl has to agree with the ds that we've chosen. So direction must agree with our ds. And so the way we can check that is using our right-hand rule. So with our right-hand rule, what we would want is if we put our fingers of our right hand in the direction of our path, dl, we would want our thumb pointing in the direction of ds. So if we came up here and we labeled these as A, B, C, and D, for this case we would want our path L, if we were using ds1, we would want to go from A, B, C, D, and back to A. So counterclockwise, such that with our right-hand rule, our thumb is then in the direction of ds1. So just briefly, let's set up what that integral would look like. We're not going to solve it, but we would have that our overall flux is equal to, of course, the line integral around that closed path of A dot dl, but that's not very useful because we have different dl's depending on which of these four segments we're on, right? So this segment is going to have a different dl than this segment, different than this segment, different than this segment. So sort of thinking back to when we were in our vector algebra, our vector calculus unit, we can break this up and we can say this is the integral from A to B of A, and then along that A to B segment, our x is changing. So this is going to be dot dx in our x direction. Then we move to that next segment, so that's our B to C. So in this segment, only our y value is changing, so we have dy in our y direction. And then our third segment is going to be C to D. And here we're changing in our x, and we're actually still going to leave it as positive dx in our x direction. And then for our final segment, we are going from D to A. And so we still have A dot dl, and now we're only changing in y, so we have dy u of y. And so again, as I sort of pointed out, both of these are positive values. So as you might recall, our dl is always going to be positive. So dl is always positive, and then we let the limits of integration take care of any negative signs. So limits of integration take care of our negative signs. And so we've looked at examples with that previously. As practice, you could solve for this flux using this alternate form, and of course you would expect to get this same 20 Webers that we got with the other form of the equation. So one last thing I'll note is if you do want some extra practice using this alternate form of the equation, you can see example 7.7, which is on page 323 in the textbook.